thank you, Vivian, for the introduction. This being live streamed, so that's okay. Yeah, so let me maybe review for people a little bit, if they missed the first talk, what we talked about last time. So we are trying to build a boundary at infinity. As Ruth explained, the boundary at infinity is all the ways you can go to infinity, but our goal is to generalize the Gromov boundary, which is for hyperbolic spaces. So we want to like capture the hyperbolic directions that are going to infinity. And our candidates for such things were the directions that are sublinearly Morse, right? So let me recall what that was. So the sublinear Morse basically means that you have this dichotomy that either you are in a fixed neighborhood of your geodesic, right, the sublinear neighborhood, but the moment you leave this fixed sublinear neighborhood, then you diverge linearly, right? So as long as this behavior is always forced, that you either in this fixed sublinear neighborhood or you diverge linearly, these are the directions that we decided are hyperbolic. So let me just write that with some more notation. So as usual, we have a XD, which is a metric space, a proper geodesic metric space. We have a point O here, which is our base point. If I say a ray, which could be a geodesic or a quasi-geodesic ray, let's say so B is some function like that to X. With an isometric embedding. So if I write beta, usually I mean it to be quasi isometric embedding. So these are geodesics and these are the quasi-geodesics. I'm always assuming that the base point is the beginning of the ray. This is a 0 and this is O, which is our base point. Okay, so this is so we pick an object which is a geodesic or a quasi-geodesic. Also, I always confuse a geodesic with this image. So a geodesic is a map from something to something else. But you can look at the image, which is an object, it's a subset of something, right? So I can kind of think of B as a subset of X. And then I can say this is the contracting or Morse or something like that, right? So this is the abuse of notation, which I usually do. Then I can look at the neighborhood of a geodesic, right? So this is a M neighborhood of a geodesic. So this is all the points X. The distance between X and B, which is a set now, is less than or equal to M. Right. If I put a kappa in here, then I can look at the kappa neighborhood. So basically, kappa means you replace 1 with the sublinear function kappa. So you get the same kind of thing. X in X, where the distance between X and B is less than or equal to M times kappa. But kappa of what? So kappa of norm of X, right? So let's recall norm of X is the distance between the origin and the point X. So the picture you should have in mind for these objects is that you have a B and you have some sublinear function where the thickness at each point, say X, this distance has to be less than or equal to M, which is some gauge for the neighborhood, how large the neighborhood is, and kappa, which is our gauge of how small the sublinear function is. Maybe I should say what kappa is. So kappa is usually a sublinear function. So it's a map from a 0 infinity to 1 infinity. So I like the kappa to never be 0 because I keep multiplying things by kappa, and I don't want that number to be 0, right? So the kappa is at least 1. So this is a continuous, maybe concave, sublinear function. Continuous.
So are you considering a fixed kappa once and for all?
No, but that's why the kappa is proper notation.
Right.
Right. So I mean, like, but if I write kappa as a sublinear function, and I can play around with different sublinear functions, no, right? But you know, if you want to have a sublinear neighborhood, you have to choose a sublinear function, right? And then after that, you can also have like a gauge for that. Like, so there are various sublinear functions in the same class of sublinearity, but with different thicknesses, right? So this M is kind of the thickness of the sublinear function. Like if kappa was 1, I just get a regular neighborhood, but I still have different sizes of neighborhood, right? So the neighborhoods grow by kappa, but still they can be large or small, right? And this M tells you how big or small they are. Right. Okay.
Thanks.
So yeah, go on. Any more questions? I heard something. Okay. Continuous, concave, and sublinear. So the limit of kappa of t divided by t is 0. So this is the notations that I'll be using. So I can write things kind of down more formally and easily using this notation. Anything else about this? So why do I pick this to be concave and continuous? You don't really need to, but why not? You can always make any sublinear function concave and continuous by growing it up to a factor of a constant, right? Just take the convex hull or something. Like if you're doing something like that, you just like make it be concave by making it a little bit bigger. So it's not a big problem. These are just for convenience. Any sublinear function works. Okay, so I'm gonna erase this. Is everybody happy with all the notation? So we're not gonna repeat all this. This is always assumed. So what was our definition of the sublinearly Morse? It was, so we would say B, which is a geodesic, remember, is kappa Morse if you have this dichotomy that you're either linear or you stay in this exact thing, right? So if there exists, so let me just do every QQ, there exists the MQQ. So this is you have to have that because your sublinear neighborhood has to be larger for the Morse Qs, right? If the quasi-geodesics become more wobbly, they're gonna like stick out a little bit. So that is unavoidable. Okay, so you're saying kappa Morse if for every R and kappa prime there exists kappa. Sorry, there's R prime, actually it's called capital R, such that it's the distance. So for every beta, this is a quasi-geodesic ray, right? Q, geodesic ray. So now, after all this notation, we can write what we want. So if beta of T has a distance less than kappa prime of normal beta of T, actually, let me do it like that. This is better. I will explain what's going on here. So that means dx of beta of TR and B is less than or equal to kappa of R. Okay, so it's kind of like a mouthful, this definition, right? With all the quantifiers and so on. But the picture-wise is clear. You have a B, let's say QQ are fixed, then you pick a particular neighborhood of this, n kappa b m of QQ. So there's a neighborhood, a kappa neighborhood, depending on the QQ, such that the following thing happens. The moment you leave this, you have to go away linearly fast, right? But I have to write this down somehow. So I want to say that if I pick somebody that much further on happens to be kappa prime of r close, so at a distance r away, then at the distance little r away, it's actually a kappa of r close, well, times m. Yeah, right then. So if you are sublinearly close later on, you have to actually have been in this particular fixed neighborhood, but by just changing the r to a smaller r. Okay, what is this TR and TR? So this is the ball of radius r. The TR is the time where beta hits the distance r, right? And this is beta of t level r. Yeah, so we spent like yesterday talking about this. Hopefully you'll see today that this definition, even though it's kind of long and complicated, is exactly what we need. So at every step of every proof, all you need is to apply this definition and you get what you want, right? So that's what I'm going to show you. Okay, so this is our definition. So, right, so we have the notion of kappa Morse. I'm not going to write this definition down. From now, I'm going to draw this picture. I'm going to say, oh, you're sublinearly close far away. Therefore, you're kappa close earlier on, right? So this is what the definition gives us. Having some control later on gives you some uniform control earlier on. Okay, which is the same way of saying that if you had left here now, by this time you'll be really far away, you'll be linearly far away. Okay, good. So I'm going to erase all this. So this is also a review from the last time, but yeah, I mean, maybe actually do one more notation. Instead of writing things like that, sometimes I write like B restricted to R is contained in N kappa B and QQ, right? These are kind of the same. Well, actually, this is what I really want, not just that. So this B restricted to R is the restriction of the quasi-geodesic beta to the ball of radius R around the origin. So I want the beginning of it to be contained in the kappa neighborhood of the geodesic B.
Okay. So it looks like the big R also depends on your choice of geodesic B. So if I give you a different...
Correct. That's correct. Right. The big R depends on the choice of beta and the little r. Yeah, it does very much, right? It does. Yeah. Right. So all this together, like all this information, this function that relates to this guy, it'll tell you like how Morse this guy is or something, right? So you're right. So in reality, like a function that comes with the definition of Morse. Okay, good. So now we want to, so the goal for today is to define some topology. So I'm, even though the talk is kind of short, but so I'm going to spend some time telling you what not to do, especially since this question of the first countability and the what's wrong with why is the Morse boundary with the original definition not metrizable? Like I want to see like what are the pitfalls of defining topology before drawing down my definition or something, a definition that I think is best. So let's see what is how to define topology between a coarse object. So remember, our topology should be basically visual topology. Like that's the Gromov's topology, like to just say how far things travel each other. That's what we want to do. We want to have sublinear error terms because that's what we are doing, right? And we want to be quasi-isometry invariant. So the quasi-isometry, so the definition should be somehow natural, that when you put it through a quasi-isometry, it's robust, right? It kind of stays the same. Excellent. Yeah, I see some chat things are going on. Again, somebody should be in charge of telling me if there's a good question in chat that I need to know. Please interrupt me. I'm happy to answer. I'm sure somebody.
So there was a question about can kappa equal to 1?
Yes, kappa equal to 1 would be just the usual definition of Morse, right? So if kappa equals to 1, it just means anybody who is sublinearly close has to be uniformly close. So this is actually equivalent to being Morse. Like at least it's stronger than it, but it turns out to be equivalent to it. Because if you have a quasi-geodesic like that, you can, with some shenanigans and complication, you can think of this as a kind of a infinitely long quasi-geodesic, which maybe contains this or some parts of this, right? And then you can say, well, look at this guy. This is sublinearly close to be kind of farther away, so it has to be uniformly close. So in particular, it implies Morse with some amount of argument. Right? Yes. So kappa equal to 1 means just Morse. And that was a picture of a boa eating an elephant. Anyway, so let's move on. So the question is what not to do. So in particular, so what is wrong with this? There is nothing wrong with it, of course, but what are the issues that come up with? Why is the Morse boundary
There's a
yeah.
There's more question regarding the definition.
Yes, go on, please tell me.
Was R independent of beta?
No, yeah, the R depends on beta. Robert also asked that. So yeah, so I have, on dependent on beta, you mean? No, it depends on, yeah, I forgot which one was B, which one was beta. It's independent of beta, yes, it depends only on B. So it's a property of B being Morse, right? Property of B being Morse means any quasi-geodesic. So for R, there exists a capital R such that any quasi-geodesic that is kappa prime close at time R is going to be M kappa close at time little r. Yeah, independent of beta, but depends on B. Yeah, maybe that wasn't clear in the definition. Okay, so these are good questions. Yeah. So all this is like a property of this particular guy. Okay. So Morse boundary with the inverse lemma topology. So let me explain what this was. So here is basically you were looking at the Morse geodesics only, right? So Morse geodesic. So let's say you have a Morse geodesic, and then you have a bunch of other guys converge to it, and really you want your convergence to be like a Gromov convergence, right? So since these guys are Morse, you don't have to really worry about anything. So the convergence is basically like a visual convergence, right? But then you do it for each Morse gauge level separately, and then you take the union of all these guys, right? So as was discussed before, like as the Morse gauges go to infinity, then the geodesic doesn't converge to anything. So what is wrong with that? What is not that what is wrong with that? What is the issue that comes up from that? Like it's not metrizable for what reason? So what is the nice property of the metrizable space? Like if you have a metric someplace, let's say you have a point X, and you have different sequences converge to this, maybe like sequence X11, X12, and so on. And you have another sequence X21, X22, and so on. So let's say you have infinitely many sequences converging to the same point. You can always do a diagonal argument. And this comes up pretty frequently, that you can pick a point in each one of these guys, and this will converge, right? Because if there's really a metric in here, you can wait for each sequence to get close. And if you do that, then you converge, right? So remember, if XD is metrizable, and you have Xij converging to X, right? As I goes to infinity for every J, then there exists an index Ji, depending on J, such that Xj ij also converges to X. You can do the diagonal argument for metrizable metric spaces, for metrizable spaces or for metric spaces. So this is what fails in the Morse boundary. How it fails is like, let's say you have somebody who is very Morse, and you pick a sequence of geodesic xi, j, that the j is like a Morse gauge of these geodesics, right? And I is how much they fail travel. Let me actually make this very, very precise. It's going to be a random thing. I'll make a very weird metric space, pick array, because I don't need anything else, right? And in each integer point I, if you have 1, 2, I, pick a stick coming out, attach to this plane, and in the plane maybe have a whole grid, and at each grid point have like a line coming out. Okay, so this is my weird space that I just built exactly for this example. And I can make this xij, the path, maybe called bij. So the path bij to be something which goes forward I, goes up on the ith thing. See, each one of these guys have their own plane, right? And then here it travels some random direction, distance of j, and then goes up. Okay, so pick some object like that. All right, so if I fix j, see the amount of time this guy is spending in the flat is bounded by j. So these guys are Morse, and the Morse gauge goes to infinity as j goes to infinity, right? With all practical purposes, this the bij's are converging to b as I goes to infinity, right? Because this guy is Morse, they're following this very much. If you pick any quasi-isomorph, there's no way to separate these guys from each other, right? So the bij's are converging to b, but bij's are less and less Morse as j goes to infinity. But that's for reasons that happen later on in life, right? Okay, but with this inverse limit topology, you penalize that because you define topology at each Morse gauge level separately, right? So as j goes to infinity, if I pick b j ij, right, and look at this as j goes to infinity, the Morse gauges of this geodesics is going to infinity, and this converges to nothing, right? So that's what people mean. They said there are too many open sets. Like you separate this sequence. What does this sequence do? It's a sequence which spends some amount of time here, goes up later on, is being less and less Morse later on, and does something else. And you know, in that topology, this will not converge, which is geometrically sounds a bit unreasonable. Because these guys are Morse and they're fair traveling this really well, and there's a narrow neck here. There's no way to separate these guys. These guys should converge, but they don't. So you have all kinds of sequences which look more and more like B, but they don't really converge to it, right? So the diagonal one doesn't work, so therefore it's not first countable. And if it's not first countable, it's not matriceable. So we don't want to penalize a geodesic for its behavior later on. So later on, this guy is spending some time in the flat and is being not Morse, right? But this is not a problem. Up to this I level, this guy is really following this one in a very narrow way that it cannot be separated. So we would like, in our topology, we would like this sequence to converge. Right. So just because the Morse gauges of these guys are blowing up at a later time, I don't want to just create open sets separating those guys from my original. Okay, so that is one thing to keep track of. There is the opposite issue, which I'm going to talk about. Is there any question about this example? Okay, so there is other issue that sometimes you feel like you are converging, but really you shouldn't be. So let's talk about that. so this is an example by I learned from paper of Chris Cashin. So let's just do this kind of like these things actually show up. I mean, the examples sound like kind of artificial, but you can actually build normal spaces which have these properties. This is going to illustrate what's going on. So pick R2, remove a particular disk from the center of it, right? So you have the usual. So this is a R2 minus a unit disk. And then I attach a hair at every grid point. Right? Okay. So union hair. And then I take the universal cover of the whole thing. Right? So meaning, well, the fundamental group is Z associated going around here. So taking universal cover just means it's like a parking lot situation. As I go around, right, I spiral like that, and there's like flatness coming out of everywhere, and there are hairs coming out of all these flats, right? So this kind of situation. Okay, so it's a universal cover of R2 minus a disk union hair, right? So as I go around, things happen. Okay, so now pick a different sequence of things. So first of all, there is a particular geodesic. So let's say this is your base point O, right? And I can just go around this way. I guess I'm going down as I turn left. So let me go right to go up. Okay, so call this A. It's a geodesic. So A is the geodesic going up the spiral. Okay. So A, note that is Morse in this space. So why is A Morse? Because if I pick any ball and I project it, doesn't matter how big the ball is, the projection is going to be length less than pi or something, right? It's the guy goes around. So the balls, no matter where they are, they project only to some small part of this. You don't have a ball that spirals around, right? So it's contracting. Contracting implies Morse. So alpha is very Morse. So it's one of the things that we like. And then we can pick a sequence of things whose Morse gauge is going to infinity, kind of like similar to before, right? So I pick a bunch of Morse guys which do the following thing. So maybe I'll draw them over here. It's easier. So I want to pick things which go around here n times, but then go away and then go up the hair, right? So you go around n times and you go away, like say 2 to the n distance, and then you go up some hair. Okay, so beta I, so goes around n times, then forward 2 to the n distance, up. This is a nice quasi-geodesic, right? I mean, you can, it may even be geodesic. I mean, like at the end, you can shortcut it a little bit, right? Maybe if I just go from here tangent and up, I'd be basically geodesic. This is a really close to being a geodesic, kind of quasi-geodesic, okay? Okay, maybe we can make it be a geodesic. All right, so if you look at them, at the visual topology, which means if I just keep track of how far the beta i's are fellow traveling alpha, right? So beta i's seem to be converging to alpha, right? Because the alpha goes around the whole time, and these guys go around the whole time. And in fact, beta i's are all Morse. Forget about the sublinearly. Like all these examples already show up for Morse geodesics, right? Okay, but I don't think these guys should really converge to alpha, right? So I want to convince you that this is a bad idea. Having this beta i's converge to alpha would not be a good idea. So why is that? Because I can apply a quasi-isometry to this picture and make this beta i's not converge to alpha at all. Right? So there exists a quasi-isometry phi, like of R2 to R2, that sends like a straight line into a spirally line. Actually, maybe I want a spirally line to the straight line, right? That would send, pick a spirally line which goes around n times and lands at a 2 to the n, right? And maps it into straight line, going from 0 to 2 to the n. Use some color. So start from 1, look at the exponential spiral. This doesn't look exponential, but this is like 2 to the n minus 1, 2 to the n minus 2, and so on, right? So every time you go around, your radius doubles, and I can send this to the straight line. This is a homework you should do on yourself. Such a thing exists, right? Because it's exponential, right? So even though it looks like you're spending lots of time going around, the amount of time going around and distances are the same. This is a quasi-geodesic, and this one's a quasi-geodesic. You can send them to each other, right? Such things exist. Like R2 is flexible like that. It's not very rigid. You can do craziness like that. Okay, so that's one observation. The second observation is that I could actually replace this beta I with equally nice quasi-geodesics, which don't go around exactly, but they kind of do the exponential spiral and go over here, right? So I can look at the beta I prime, which spirals, then goes up. So the beta I prime and beta I prime should be in the same class because the ends of them are the same. They're the same way of going to infinity, right? They represent the same point in a boundary for any reasonable notion of the boundary. But if I apply this phi to this beta I primes, they just become sequence of straight lines going up and going to infinity, right? Then these guys do not converge to alpha in visual topology. So it looks like if I pick visual topology as my topology, right, that is not good because things which look like they're converging in a visual topology can be sent to things which are not at all converging in the visual topology. Can Frida also hear me? Yes. Okay, we have good guests. Right. Anyway, so this is the other thing to worry about. So again, what is causing this? The fact is that these beta i's are Morse, but the Morse gauge is going to infinity. But it's going to infinity kind of near where the convergence is happening, not later on, right? It's happening like exactly like when I'm looking at if these guys are following each other or not. Like they look like they're following, but they're leaving some flat. So they're really not following at all. So you have to reconcile these two issues and come up with a notion of topology which kind of does what you want, right? You want to say, well, if two things are kind of like look like Morse up to some near error and they're fail traveling each other, then that's real, right? So I want to count that. If you're fail traveling, but that part of you is not so Morse, like you can be like pushed away, that doesn't really count. But of course, if your Morse gauge goes to infinity for reasons that are happening much, much later in life, that's not a problem. So we want to like glue all this together into one sentence and define a boundary. And I want the boundary to look natural, basically to be, the definition should be the same as the visual boundary, right? With sublinear errors, right? Okay, so that's the goal I set for myself. Any questions about these two examples? Maybe in the chat or otherwise, yeah.
So how fast does this logarithmic spiral go away with respect to arc length?
How fast? Say it again.
Yeah. So how fast is the yellow one moving away with respect to arc length?
The arc length is linear to n. So every time I go around, my length is pi times. Yeah, what do you mean? Like, it's pi times 2 to the n at most.
Okay. So it's much faster than.
Yeah.
Okay.
Yeah. Oh, I see. Yeah, that's right. So the green guy is not flow traveling. Yeah, that's a good point. I understand what you're saying. So the alpha and the green ones are not sublinearly flow traveling. Exactly. Right. So there's the orange guy who is very closely flow traveling alpha. Like it's attached to it. But the orange guy is the same as the green guy. And the green guy is linearly flow traveling, like he's going away linearly. So basically, I can replace the orange guy with some other guy who is not sublinearly close. And that's exactly, so that you're getting the correct point. Yeah. So that's exactly the problem. So it's not enough for the guy itself to be close. Every other quadratic in the same class has to also sublinearly flow travel, right? So I need to say all the quasi-geodesics representing the same class have to sublinearly flow travel. So that is exactly the solution. Right? You cannot just look at one quasi-geodesic, you have to look at all quasi-geodesics. If there is a way to go away linearly, then those guys are out. Yeah, exactly. So let's write this down in a sentence. Yeah, perfect. So Robert gets the topology already. Okay, so how do we define topology? So that, mechanically you have to define open sets. Open sets are kind of hard to define in this setting. They're too precise, right? So nobody does that. So what you really do is you want to define neighborhoods. Remember, a neighborhood is basically like an open set plus a bunch of junk attached to it. Maybe it's not even connected, so some craziness like that. But as long as it has an open core, it's an open neighborhood. Right? So let me just say we define topology using a neighborhood basis. But I have to go kind of slowly. So first, let's see what the set is. So I fix kappa for now, right? Actually, forget about the fixing. Even before that, I need to do something. So what are the points? So let me first define an equivalence class between the quasi-geodesics. Again, our category of thinking, like in the way of thinking, is that the sublinear functions are the same as bounded function. The Gromov boundary is geodesics up to flow traveling, so it makes sense for us to do geodesics up to sublinear flow travel, right? So first we define, so let's say alpha and beta are quasi-geodesic arrays. We say alpha is equivalent to beta if the distance between alpha and beta divided by t goes to 0, and the distance between beta of t and alpha divided by t goes to 0. So if they are sublinearly far away from each other. So it's clearly symmetric and transitive, right? So this defines an equivalence class and now I can fix my kappa, and then I notice something very interesting, that if alpha is kappa Morse, and if alpha is in the same class as beta, then beta is kappa Morse. That's the first part that you would see, like maybe you're doing something right. So if you have a natural notion of class and you have a definition of some kind of geometric property, it should at least be preserved by the class. Let's see, how do we prove such thing? Well, alpha, beta. We basically invoke the definition, and it should be immediate if our definitions are correct. Let's say I know alpha is Morse, right? So alpha and R are given to me, right? And I want to prove beta is Morse. So pick some gamma that is kappa prime close to beta, right? Well, the beta and alpha have their own sublinear function. So beta is some kappa double prime close to alpha. Therefore, gamma is kappa plus kappa prime close to alpha. If kappa and kappa prime and kappa double prime are both sublinear, their sum is also sublinear. So I can use that sublinear function to find an R such that if you're kappa prime plus the kappa double prime close to R, then you are kappa close to alpha. Also, beta was kappa double prime to alpha close. So beta is also kappa prime close to alpha. So this is kappa and this is kappa. Therefore, the distance between gamma and beta is at most 2 kappa and I'm going. Right? This is the kind of argument. So see, the definition kind of fits into this perfectly. Like, if you're sublinearly close later on, you're kappa close. And if I have two of them, I can just do triangle inequality and kappa plus kappa is still kappa. Right. Okay, so the property of being kappa Morse is a property of the class of quasi-geodesics. Okay. Yeah, I'm going to erase. I give people chances. I see lots of chats, but people will shoot in Rafi. You can also just speak up. This is not an official lecture, so you can just talk. You don't have to write in chat. All right. So very good. So with this in mind, then I can actually define the points on the boundary. Right. So the kappa boundary of X as a set is the set of classes of kappa Morse geodesic. Okay, so an element in here I write with like boldface A or something, maybe with the underline, right? And then the geodesic in here I write as A, and the quasi-geodesic I write as alpha. So elements in here, maybe I write A and B like that. All right, so now we have to define a neighborhood basis. So I will define this U set, and then I use it to define neighborhood. So like pick a A in A. So this is geodesic representative of this class, and then I define U kappa A R to be the set of. Well, maybe actually let me do. Yeah, that's fine. The set of classes B, right? And now we kind of know what to do, right? So I don't want just the geodesic in here to fail travel this particular geodesic. I want every quasi-geodesic here to fail travel that. But of course, that's impossible because quasi-geodesic, the Q could be already larger than R. Right? If your additive error is larger than your radius, then there's no way to control it. So you have to say that the Q has to be small compared to R, right? So every Q and Q, small compared to R. I'm going to tell you what that means. So what I want is, and for every beta in B, which is a QQ quasi-geodesic ray, right? I want the restriction of B to R to be contained in kappa neighborhood of this A. with the Morse gauge that depends. So remember, A is kappa Morse, right? Which means it comes with some Morse gauge. You will just write MA of QQ, which says that the QQ guys have to be this close. So yeah, so we have done the work before. So here our thing is kind of natural. I'm just saying that so for this guy to be close to A, for B to be close to A, every quasi-geodesic in B has to kappa fail travel A up to distance R, right? But of course the Q's have to be small. And what does this mean? It doesn't mean much. It just means this MA of QQ has to be much smaller than R. So let's say R divided by 2 kappa R. I think this is what you need. So it's kind of like, this is your error term. So I want this to be smaller than R basically, but after multiplying by the error term. Okay, so it really doesn't matter what you pick in here, as long as, because you pick this, if you have nothing in here, the Q is going to be bigger than R. That's not good. So the Q have to be smaller than R. But that's kind of how you should do this. Okay, so this is a definition of the U, and then I define a neighborhood basis of A to be the set of all subset of the boundary, right, such that U AR is a subset of W for some R. I mean, you have to, this is a neighborhood basis around the point. I mean, basically, if you have a neighborhood, if I make it bigger, it's still a neighborhood. To be a neighborhood just means you have some core open set, right? So these are the guys I use as my basic things, and then I can extend them to any bigger set. So any set that contains one of these is what I call a neighborhood of A. Okay, so maybe I'll look this part up to make sure I don't miss anything. What do you need to know about neighborhood basis to say that they define topology? Let's write it down and see if we can check them, right? So for every point, you have to have a basis of things, right? So one thing that you need, that the A has to be inside of every, so for every W in BA, the A has to be in it. Okay, so that makes sense. You have to have this other thing. So if W is in BA and V contains W, then V has to be in the neighborhood of A. So anything that is bigger than a neighborhood should be a neighborhood. So that's also trivial. Nothing to write about that. If VI, which is a finite collection of things, are in the neighborhood of A, then the intersection of VI should be a neighborhood of A. So these three are kind of like essentially trivial. And the one that is slightly less trivial is the following, that if you have a neighborhood of A, then there is a smaller neighborhood of A, that for every point in here, V is also a neighborhood of B. Right, so what is the picture here? You want to say there is really an open core. So let's say this is V. I want to say there exists some other neighborhood, W, that if I pick, and here's A, if I pick any B in this W, it's inside the open core of A, right? So the neighborhoods really get small. So you can pick a smaller neighborhood that is inside of this open core. That's what this last one is. Okay. So this is a basic topology. We copied this from the Google Keybook actually. That if you have these properties, there's a unique topology on your space where these are the neighborhoods, right? Any question about this set? So I'm going to try to prove some of these. Maybe I'll prove number 4, right? Which is the hardest. So remember the definition of U. The U says a neighborhood of a particular point A is you pick a geodesic in this class, which always exists. You have to prove of it. And you look at all the points in the boundary where all quasi-geodesics here fellow travel A, kappa fellow travel A, up to distance R. All quasi-geodesics. Yeah, I'm not going to worry about the smallness. The Q's are always a small compared with R. You have to like do stuff to that. Okay, can I erase? Okay, let's see if we can prove this object. So let's draw a picture first. So the picture is you have your V, right, which is a neighborhood around A, and you want to find a smaller neighborhood, let's say W, around A, such that if I pick a point B, the V is a neighborhood of B. Well, what are the neighborhoods of B? Neighborhoods of B are the points which have some U, B, R in them, right? So, well, if I pick a V, I might as well assume it's kind of a U, A, R of something. I want to find the smaller neighborhood such that any point in here, if I pick this, is going to be in that. So let's just write this down. I could pick all of these guys to be of the form UBR, right? Because I can expand into something bigger. So what this says, basically, this last one says that for every R and A in the kappa boundary, so I'm saying that this big one, I'm going to think of it as UAR. This other guy, I'm going to think of it as UAR prime. And this one, I'm going to think of it as UBR double prime. So I'm going to retranslate this picture into this U language and see what it says. So for every A and R, I have to find R prime, such that for every B in U A R prime, there exists an R double prime, such that this whole thing is a subset of that, which means for every C in U B R double prime, I have C is in UAR. Okay, so this fourth sentence is that. So let's say it again. For every neighborhood, there's a smaller neighborhood of B. There's a small of A. There's a smaller neighborhood of A. So this is R. Such that for every point B, there's a smaller neighborhood around B. But for every point C, C is in the original neighborhood. Right? That's all I have to show. It sounds kind of complicated. Let's see how this definition of the sublinearly Morse that we have helps us to prove exactly this kind of sentences that we need, right? All right, let's get to it. So I pick A, which is my original guy, and I have some distance R. All right, so pick R prime. We don't know what it is going to be at the moment. Well, it's going to be something. So let's not worry about it. We're going to see what we need from it, right? And then we are going to pick somebody in here. Let's call it B. And I'm going to pick some R double prime, and I'm going to pick somebody close to that. C. To prove, this is what I want to prove, that the C is in R neighborhood of A, I have to prove every quasi-geodesic in the class C is in kappa neighborhood of A up to distance R, right? So let's choose gamma. Pick gamma in this class C. Okay. Since gamma is in class C, I can pick this R double prime so small that this gamma is, well, B itself is kappa Morse. So there's some Morse gate associated with that, and I can pick this gamma so that it is kappa times MB close to B at R double prime. Well, I don't even need this R prime so much. Seems a bit easier than I expect. Yeah, this is for the metrizability that I need to do much more work. I think here is very easy. Is that right? So what I know is that the C is close to B up to R double prime. So there's a kappa prime MB. Okay. But also I know that the B is close to A at R prime. Yeah, can't I pick R double prime equal to R prime? Yeah, maybe I can. So then the B is also kappa time MA close to A, which means gamma is MA plus MB times kappa close to A at this time R prime. But the sublinear Morse says that if you are sublinearly close at some further time, you're going to be fixed close at some earlier time. So even though I introduced this MB times kappa to it, this is still a sublinear function. So the distance here between gamma is just going to be MA dot kappa, which means C is in UAR kappa. Okay, so to keep track of all the constants and write this down is a bit of a work, but really not so much. Right. If you're close to here, you're close to here, you're sublinearly close, not with the perfect sublinear function that I want, with some sublinear function. But I can always reduce the R to be perfect. Like all the error terms can be always killed off by just going back a little bit. You just add all this stuff, you have all kinds of error terms, and then they all disappear by just going back. The magic, like magic. Right? So the proofs just work almost with no effort. Okay. We have time, so let's get into it. What do we need to prove some kind of, so this is basically it. So you have these properties and you can define topology, right? So yeah, the open sets are defined to be points where there's a neighborhood that is contained in them, and so on. Yeah, everything kind of works out. Yeah, let's go into the metrizability. So there's one part of this that you have to be careful with to prove things are metrizable, which means you have to prove something doesn't depend on something else. So I have to be, so we kind of digged out into points of topology, and I'll simplify it for you. So to prove the topology is metrizable, you kind of have to have a notion of triangle inequality, right? So the basic idea is like this, that if I pick a point X, A, and I pick a point B, and their neighborhoods kind of intersect, right? Then this somehow should, if you are metrizable, there's a triangle inequality, this should somehow mean that the B is close to A, right? So you need a sentence like that. There are many different ways, like the same hyperbolicity, like metrizability is also like that. There are many different ways to do it. And then usually, like if you pick one key property and prove that, then that's enough to prove the whole thing is metrizable, even though you don't get a metric, and yeah, it comes with also good topological property. So for our purposes, this picture kind of translates to something like this. So for every beta and R, there exists R prime, such that for every alpha, there exists R double prime. Actually, maybe I pick this guy to be geodesics if you don't guys don't mind. A, B, such that if C is in U alpha R double prime intersect U, I'm putting A here, U B R prime, then A is in U. Okay, and the important part is that the R double prime doesn't, yeah, so, and the key point here is that the R double prime depends on A and R prime only, and not on beta and B. Okay, so let me draw the picture again. So so here it means, I'm going to erase that. For every B and every R, there exists an R prime. R prime is going to be named of that, so it's correct. So for every R, there exists an R prime, such that if I pick any A, there exists for every A, there exists an R double prime, such that, so this is A, such that if a point C happen to be the intersection of this R prime and R double prime guys, then A, which was here, this is A, this is C, A is actually in the original set. So any open set of size R double prime that intersects the ball of radius R prime around B has to be contained in this bigger ball of radius R around B. Right? So I think of these R's are radii, but they're not. They're like these distances forward, but they're kind of the same. The bigger the distance, the smaller the radius, right? So I'll write the radius R, but the reality, the bigger the R, the smaller the neighborhood. Okay. Any question about this? So yeah, it boils down to this kind of sentence, which is kind of basic triangle inequality. If somebody is close to A and close to B, then A and B are close in some uniform way. Right? Yeah. Okay. So that's all you need. So let's draw a picture of this and see if we can prove it. So we have should be the same picture as before. We have a B and we have an R, right? And we also have an A, and we have so for B, we have an R prime, and for A, we have an R double prime. And then somehow in the middle, we have some quasi-geodesic gamma. Oh, actually, no, you have a C. So we can pick the C to be a geodesic. we have a geodesic C that we know at R prime is close to that, and at R double prime, and R prime is close to that. Our goal is to prove that A is close to B, which means if I pick any quasi-geodesic alpha in the class of A, I have to prove it's close to B at, at this level. Okay, so a lot of moving pieces. Let's see if we can do it. All right. So the point is, if alpha is close to A, at this point, this is some number, MA times kappa. Since C is close to that, this is also some MA times kappa. Since C is close to B, this number is MB times kappa. So the only wrinkle here is that this R prime should depend on A and not B. If the R prime could depend on B, I could just like come back here and make everything work out. But I can't do that at the moment, right? Because the R prime shouldn't depend on B. But there's some other trick I have, is that these three sublinear functions are kind of really less than linear. So I can make this R prime big enough to make sure that these numbers are less than R over 2 at most. So I can do that. So what I do then is, since this is very close, I pick a point really far away from here, and I connect it to this alpha, and I produce it quasi-geodesic like that. This is the other trick that you have, that if distance is kind of sublinear, I can do a surgery from here and connect it somehow like that. And what I would get is I would get this quasi-geodesic alpha prime, right? So alpha prime turns out to be, if alpha was a QQ quasi-geodesic, then alpha prime is like some 9Q quasi-geodesic. So the the quasi-geodesic constant of this goes up by some amount. Right? So if this is, and this is close to B completely, which means at this point, right, it has to be MB 9QQ times kappa close to B, right? Okay, right? So this is a big quasi-geodesic, so it's going to be this close. This is not close enough. I want it to be MB of QQ. But what I would say is that now look at the original alpha. The original alpha is a QQ quasi-geodesic and is this close, which is now my new kappa prime. And I can do this one more time, right? And so if you have an alpha, which is a QQ quasi-geodesic and is kappa prime close, which is now, this is my kappa prime, then I'm going to be MB QQ times kappa close at this level, and I win. Okay, so the details of these proofs you're not supposed to get really at this speed, right? But the basic ideas are like the tricks that go into this business is that, I can play around with things kind of being close to each other later on and produce some kind of error terms. And I can play this game repeatedly of going back and making error terms better, right? Using this notion of kappa Morse. So I just want to get into it to just say like what really goes into this kind of proofs. And this is the kind of argument that goes into it. So which is why this definition is suitable for the proofs that come up with it, right? So if you're doing some other kind of geometry, maybe you want to pick a different equivalent definition and work with that. But yeah, if you just want to prove things are topologically good properties, like the definition fits perfectly into this kind of proof. Okay, so yeah, I have a few more minutes. Are there any questions? Yeah, I mean, I don't